And it says we're recording. Ara, how are you?
I'm good. How are you, Sean?
Not too bad. I appreciate you doing this. I know you're running a department, teaching classes, taking care of your dog, working from home, so you're trying to stay sane. All the things that have gone on, even though we're recording this at the beginning of 2021, there's still carryover from the craziness of 2020. So I really want to thank you for doing this. I've looked forward to this since I started bugging you so many months ago about this.
My pleasure.
So, and I want to thank everybody for tuning in. If you're a returning visitor, much appreciated. Your patronage does help promote the channel and then hopefully grow it. And if you're new, be sure to hit the subscribe button. And if you like this video, be sure to hit the like button. And if you do subscribe, click on the bell so you'll get notified each and every time we post a video every Thursday morning. Just for a quick refresher, I am Sean O'Rourke. And you're watching actually, Did You Know That? ? Which is a channel that I started so that I could talk to interesting people about interesting topics. And this is one of my geek topics today. So bear with us if we go down the rabbit hole. And when I'm not doing this, I'm a cyber liability consultant for an insurance brokerage in New York City. And I essentially prepare companies to be hacked. Now, Ara, you're going to tell the fine folks what you do.
Thank you. Yes, I'm a mathematician, and I work for CUNY, City University of New York, at Hunter College, and I have a joint appointment with the Graduate Center, which is where the PhD program is. So I'm a working mathematician, and that means a lot of different things. So, and probably to a lot of different people, it means different things.
Well, to me, it means that I get to pick your brain about certain obscure and potentially irrelevant to most of the people watching this topics. But again, it's all about me, what I find interesting and fascinating. So before we get into what you do and how you can even try to envision what you're trying to achieve and whatnot, the first thing I always ask people in the sciences, were you always good at what you're doing now? So were you always good at math? Or is it something that you had to work really hard at to get good and to where you are?
Yeah,
and I mean beyond addition and multiplication and all that.
Right.
I'm talking about advanced mathematics.
Right. I think the answer to that is it's very individual based. I think it depends on the mathematician you ask. There's no universal statement you can make. In my case, in the early days, math was very easy. But math meaning doing grammar school or high school work, it was fairly easy. It came easily. On the other hand, once you start getting into what mathematics is really about, which is this world of ideas and building structures, that's very hard, no matter who you are. And I would say it's taken a lot of work to get to this point. I work very hard, and I think that's the main point. And there's a level of curiosity also that drives all this. And I think if you want to make a universal statement, I think one thing about us as mathematicians, we tend to be on the obsessive side. So if we get a hold of something and we want the answer to it, we'll just keep digging. And that was something I always was. No matter what I did, if I got obsessed with it, if it was something that I focused on and got obsessed with it, I would just keep that crank going until I got somewhere.
Well, I mean, that's a good trait to have, I guess, no matter what you're in, but particularly for what you're trying to uncover. And as everybody knows who watches episodes, I always have a list of questions with me, but I tend to break off when somebody says something. And you did just say something interesting that I hadn't written down. You said in terms of learning what mathematics was really all about. So for those of us who didn't advance beyond maybe AP Calc or maybe calculus 1 and 2 in college and couldn't wait to get away from math after that. When you decided to pursue this as a career, what did you learn that mathematics was all about?
Well, I think the first place where you start to see that mathematics is really about ideas is in calculus. You start to see the idea of a derivative or an integral, and that's saying something about infinitesimal structure. And that's sort of maybe the first time. I mean, it depends on your formal training, because it's possible you did see some other interesting kinds of mathematics. But before that, in general, most people who have studied math, who've taken mathematics courses, it's viewed and it's taught as rather rote um, uh, work and not anything about ideas. And in fact, that's far from the truth. Mathematics is all about ideas. And I think the first place you see that is in calculus. And as you go further through calculus, you know, by the way, calculus is one of the great achievements of mankind, humankind. It really is. It's amazing what it's done. You can't have buildings. There's no engineering without calculus. There's no structures. There's nothing without calculus in terms of architecture.
Well, above and beyond the rudimentary sort of, you know, whatever the Romans and the Greeks built. You have no skyscrapers, you have no Guggenheim Museum and whatnot.
That's right.
Nothing artistic like that.
That's right. That's right. So you start from there, and that's where the world of ideas you're starting to see in this calculus world, and then you keep going and you go deeper into structure, and there's lots of different aspects of mathematics. And when I'm talking about mathematics, I'm talking about now, and you alluded to this earlier, not addition, multiplication, and that stuff. I'm really talking about this world of ideas and structures. There's geometry. There's a heavy geometry, and I'm not talking about the usual kind of geometry you learn in high school, which is Euclidean geometry. There's more sophisticated structures. And then there's topology, which is the study of continuously moving objects and shapes. Then there's number theory, and number theory is this old, rich area of mathematics, pure mathematics, which got heavily developed. You mentioned earlier,
yeah, before we started,
before we started, you mentioned the Riemann hypothesis, and you know, these questions started a long time ago, and they're fascinating pure mathematics questions. And interestingly enough, that area of number theory has had tremendous application in security and digital information being transferred, and so on. So you know, it's a funny mixture. So anyway, these structures build. And I think what happened with me is that I saw calculus. That was the first time I realized here's this world of ideas. It seems very interesting, and I kept going. You go to differential equations. You study number theory. You study abstract algebraic structures, and then you start to see that at first they look disparate, and then in the end, actually, they're not. They're very connected subjects, and that's one of the features of pure mathematics. It's not like a mathematician learns this one little thing. They specialize, of course, into these one areas, but they have to have a strong basic background in all of the mainstream areas of pure mathematics. That includes areas like which are generalizations of calculus and geometry and topology and so on.
So we're going to get into your area in which you specialize, but I again, you and I had talked about this when we were out walking our dogs, because technically we're neighbors in the same building. But in your opinion, it could be fact, it could be opinion, it depends on who you talk to. Do we discover math or do we invent math?
Right.
I have my own answer to that, but I want to hear your answer, especially since you live and breathe this.
Well, you know, it's a philosophical question, really. It's not something I stay up at night thinking about. But no, truthfully, because it's sort of like sort of reminds me of, you know, you can ask an artist about form and impression and structure and all this, and the artist may say, "Oh, you know, fascinated with that discussion," but maybe in the end they just want to draw.
Mm-hmm.
You know, and it's sort of the same with the working mathematician. I want to do math because I want to discover, you know, discover or construct things. So anyway, to get back to your question, I think the answer is it's a bit of both. In my own experience, I feel like there have been times where I uncovered something became uncovered, and in my mind, it was always there.
Mm-hmm.
So there's the discovery part. But then a lot of times what happens is to get to that discovery, I had to construct a bunch of things to get there. And that felt more like some sort of structure that was built.
But
because it was my taste to get there.
Excuse me, but it wasn't built on you made it up. You actually, I mean, it's when I was in geometry, you had to do proofs
Right.
to prove that you know, that the triangle was a triangle, and you had to go through a very logical structure. I couldn't just make stuff up to fit the answer.
That's
So
right.
when you say you're constructing it, you're doing it based on some sort of rules, some sort of logical structure. You're not just taking, hey, this looks like it'll fit, so I'm just going to throw it in there and to make it work.
Yeah, that's right. So yeah, so there's the framework you have to work in, the logical structure, but the path you take doesn't have to be the unique. You know, everyone
Right.
there are different paths. Now, sometimes there's a best path you could take to get to this answer, but often the path you choose is of your doing. So in that sense, I feel like there are aspects that are not discovered that you're constructing. Um, but you know, I mean, it's a philosophical question. It's an
Yeah.
interesting one.
I believe a lot of things existed long before human consciousness. So and math is one of them. I mean,
Yeah.
2 times 2 was always 4, even if we
Yes.
weren't here. I mean, it was always going to be 4. We just now know how to count it. And so I presume that, but it's kind of interesting. So again, I'm dovetailing off of what you said as opposed to going to the questions. So is math an art form?
Partially.
Okay.
Yes.
I mean,
Yes.
advanced
There's an
math,
art.
advanced math
Yes.
again.
Yes. There is an art to it. There's some, you know, there's beauty in. I mean, actually, that's what pure mathematicians strive for. You don't want ugly math. You want pretty math, beautiful math. Is there a
So I've heard that a lot of times. And can you give people a sense? Because the word beautiful means
yeah?
to a lot of people something very visual, a painting, a person, a scene, or what have you. What does beautiful math mean to a mathematician? Does it just mean the paper's clean, or instead
Right.
of 3 steps, there's only 2 steps? I mean,
Yeah.
what
Yeah.
exactly does beautiful mean to a mathematician?
Yeah. I think that's a good question, and yeah. So I think there's different aspects to what
Mhm.
beauty means. There's the
Well, this is your show, so what's it mean to you?
yeah. But it means different things to me. That's the thing.
Oh,
Um,
okay. All
you
right,
could
that's
have
good.
an elegant theorem, a theorem that's very tight, and it's sort of uh, it's just you. So let me back up a moment before I
Mhm.
answer or
Sure.
address the beauty question. Let me just say, um, sometimes uh, you sort of there's a problem you're working on, and you work on, you know, mathematicians will work on problems for years. There's problems I've been working on for over 20 years. You know, they come and go out through my mind. I'm wondering about them, maybe make a little progress, maybe don't, maybe put it down, don't look at it for a long time, maybe make more progress, start to see what's going on and uncover something. But anyway, the point is, there's this problem and you're working toward it, and you're working, when you first start, you're in the dark. And you know nothing. You don't know what it looks like. There's this thing you're trying to get to, understand, not get to, understand. And the best analogy I could draw is something like, you know, when a biologist tries to classify plants of a certain type, at first they may not know anything about what the classification will entail. And but as time goes on, the structure becomes uncovered, and then it's sort of transparent in the end. And a lot of mathematics is like that, especially definitely for me, where I'm in the dark, I don't know what's going on. Here's this objects that I'm trying to understand how many there are. Are they all over the place, or are they very scarce? And then you start to uncover the characteristics of it, and then, you know, maybe it's a couple of years later, if you're lucky and things have gone well, and then you realize at that point you understand the structure of what it is, and it's completely transparent. And you say to yourself, how come I didn't think of that a number of years ago? It's very much like that, mathematics. It's this uncovering process, and I think that's part of our motivation. We want to know. You know,
so is that where the beauty comes in? Is when
yes.
when it becomes transparent?
Yes, yes, yes. So that's one of the ways beauty comes in, and then the other, I mean, beauty is a vague term, as you were suggesting, and
sure.
The other ways. I mean, another way is you know, sometimes you don't have the right formulation for something. You sort of say, well, this object I've been studying has this, this, and this characteristic. But then you start to realize these aren't the right, they're not exactly, they're not the tight characteristics that that completely distinguish this object. And maybe it's years later that you realize that. So that end result might be the beautiful theorem, and this early thing was just
it was the beginning stages. It was the sketch.
It was a sketch. Yeah.
Well, and I think that's where people have a very difficult time with math, is because it's not a visual medium. You may see the formulas, you may see the symbols, you may see the numbers, but to your point, when you were talking about an object, sometimes it's correct me if I'm wrong, it's a theoretical object. It's not a real object. It's not like my water bottle. It's a theoretical concept of this water bottle that you're trying to make transparent. And I think that's where people have a difficult time with mathematics, because there is nothing to visualize. I mean, let's be honest, the majority of the human species feeds off of what we see, and not necessarily what you can envision in your mind's eye. And I really think that's a lot of places where your love of mathematics breaks down with people saying, well, I'm never going to use it in real life.
Well, you know, so let me contradict what you just said.
Cool. I like that.
To a mathematician, it is very visual, and these objects are very real. So, and I don't think I think that's just getting used to the object, and that could be, anyone could do that. There's this mental picture you have of something, and the kind of mathematics I do, and a lot of the mathematicians I know, everything is visual. It's not the usual kind of visual that I draw something and you completely on a piece of paper and you completely see the object. They might say, well, I'm studying this 4-dimensional space, but so I'm going to draw you schematic pictures of it. which are sort of three-dimensional slices or
Right.
something along those lines. So actually, the idea, so this business of mathematics is made up of ideas, and putting those ideas and structures together, building them, is related to this visualization and putting these objects together visually and understanding. Part of a tight argument is understanding the actual picture. There's usually a picture associated to anything, any ideas in mathematics. There's usually a picture.
Well, I'll be honest.
If you really understand it,
you're
there's
right.
usually a picture.
But I mean, the picture to you versus the picture to me or to non-mathematicians are going to speak two different languages. Because it's
right.
I equate it to when everybody tries to represent gravity and tries to explain gravity visually. And it's almost impossible. I mean, it's just, it's impossible to do. And everybody, but you look at the explanation from a physics or a mathematics standpoint, and everybody that I know who understands it says, oh yeah, that explains it perfectly. I mean, it's exactly how I see it.
Right.
And I'm looking at them and and I think I'm the crazy one, but for them, they see it. And I think you underestimate how different you are from me when it comes to visual, when it comes to mathematics. Because
let's okay. So I want to play the devil's advocate here, because I think there's
that's why I started this channel. Very reason.
So let's take the game of chess.
Okay.
Because I think there's a lot of analogy with mathematics in chess, in many different ways. But one is, a good chess player, they start to develop a sort of intuition, and they can see ahead and visualize the positions that are coming. Okay, maybe a grandmaster can see very far ahead, but and a beginner only sees 2 moves ahead. But the point is, they have to, when you're at the chessboard, you don't have the luxury of moving the pieces around in the game to figure out what's going on. You're sort of mentally processing this stuff and visualizing it. And after a while, you start to develop instincts about what visual position visually in your mentally, what's going to work, what's not going to work. If you've ever played chess, you know this. And it's sort of interesting that you can develop this ability. And I think for mathematicians, I don't think we're as weird as it might seem. In some sense, I
was going to say gifted, but if you want to say weird, we can keep it as weird.
I think we're weird. About gifted. But I do think there's so there's this visualization aspect, but I think everyone has it, and I think everyone has this. If you have this curiosity, you can sort of develop it. Keep in mind, it's years of training.
Oh, sure.
I did undergraduate, graduate school. So there's years of training involved in this, and of course you get better at it. But I think even in the early stages, you could start to develop it and start to see what's going on. It's just, even puzzles, you're given a puzzle, and these logic puzzles or something, you start to develop intuition as to what's going on, and you're sort of visualizing what's going on. Maybe in not the usual sense of an artistic picture, but there's a different picture.
Well, let's talk about your picture, your specific picture. What's your area of expertise?
Yeah, so I work largely in an area called hyperbolic geometry, and so let me describe a little bit. Let me back off and just say something about geometry first. So when we're in high school or wherever we learn about Euclidean geometry or plane geometry, that's zero curvature geometry.
Right.
So it turns out there's also positive curvature and there's negative curvature. So spaces could have positive curvature, zero curvature, or negative curvature. And let me describe some simple examples. If you look at the surface of a basketball, which is usually called a sphere, that has positive curvature. And the way to think of that is if you're a creature living on that surface of the basketball, and if you look in one direction and look in another direction orthogonally, what you see is curves that bend in the same direction. They both go in the same direction. So that's positive curvature. The space sort of curves in on itself. Then zero curvature is one of the directions just goes straight out. You're standing at a point of the space. One direction goes straight out. The other one can curve either way. So for example, zero curvature, the Euclidean plane, both just go straight out. So that's zero curvature. Okay. So you just, that's sort of an unstable.
It's the standard graph line, basically. It's going to go up, down, left, right.
Yes. So there's zero curvature. And then negative curvature, well, the only other possibility is when you're standing at a point of the space, one of the paths you follow curves down or up, so curves in some direction, and the other direction points in the opposite. So this one might point down and this one might point up. So you might think, how do you visualize that? The saddle of a saddle has that property. If you sit at the midpoint of the, on the saddle, this way it looks like this, the curve is going up. This way it goes down. That's negative curvature. And so there's zero curvature, positive curvature, and negative curvature. And negative curvature, go ahead.
Yeah, I was just going to say, and the only reason it's negative curvature is because in one direction, the curve is the opposite of what it is in the other direction.
Yes, it's going in the opposite. It's
gotcha.
One is pointing down, the other one's pointing up, or vice versa.
Again, I learned something new every day, thankfully. I never realized that's why they refer to it as negative curvature.
Yeah. So interestingly, what happens is that in negative curvature, you expand the ball, let's say just a disk. Suppose it's like the plane, but it's negative curvature. It gets very crinkly, and you have a lot of area in a small radius. You'll develop a lot of area. There's a lot of space. Okay, so negative curvature has a lot more space, and as it turns out, if you're going to study spaces, let's just focus on two-dimensional spaces, like a sphere or the surface of a donut, which is also called a torus, or surfaces that have
I'll never be able to look at a donut the same way again now.
No, they're beautiful. Well, keep in mind that, we think of a coffee mug. It's the same shape as the surface of a donut. It's got one handle.
Yeah.
So they're the same object topologically as smooth objects that you can move
That's
around.
why coffee and donuts go so well together.
They go really well together. So there's these two-dimensional spaces. The sphere, the torus, then there's another one with two holes in it instead of one hole. There's another one with three holes. The number of holes is called the genus. And the spaces are classified at least as flabby objects with their genus. You could be genus 0, genus 1, genus 2. Genus 0 is the sphere, genus 1 is the torus, genus 2 is the one with two holes, and so on. Right, so there's infinitely many of them. And you can ask, what of these geometries that I just described, positive curvature, zero curvature, negative curvature, can you put on these spaces? How can you make them rigid, these spaces? What geometry can you put on them? Well, for genus 0, that was this, that you have this nice round thing, that's positive curvature. For genus 1, which was the torus, you could realize that by just taking a square and identifying opposite sides. And I just put a zero curvature structure on that torus because the square is flat. That's just in the Euclidean plane. And I just identify the two sides appropriately.
Does it matter which direction you cut that square of the torus / donut?
No.
So it could be up or down, or it could be straight across.
straight across, right. You still get the same zero curvature. You still can do the construction to get a zero curvature structure. And then as it turns out, and this is a big theorem in mathematics, that all of the other genus 2, genus 3, and all, they don't admit zero curvature or positive curvature. They can't. They have negative curvature. You could put a negative curvature geometry on them.
But not a zero curvature.
Right. You can't put zero curvature geometry. You can't put positive curvature geometry, but you can put negative curvature geometry. And that negative curvature geometry is called hyperbolic geometry.
Okay. And so for those out there who've now sort of glazed over and deciding, should I watch the rest of this? What is the purpose of it? Is this pure mathematics, or is there some sort of practical application of what you've just described about, the sphere and the torus, and then the genus to infinity?
Higher genus, right? So that question's loaded. There's a lot of things to say
that's why I asked them.
Right. So the first thing to say is that I, as a mathematician, pure mathematicians don't think about where the applications are. They're working toward building ideas and structures, and guided by beauty, and guided by guided by building the structures and beauty. Let me just say that. Now, what happens is there's this uncanny thing that happens, which is you've got some area of pure mathematics that was developed purely as an area that's abstract, and then all of a sudden there's an application that pops out. And to go way back, for example, Einstein's theory of general relativity, when he was working on, and he discovered that general theory of relativity, or formulated it, he needed to know that this area of geometry, he needed to know that there was a hyperbolic geometry. He needed to know that there was negative curvature, because what he was studying, general relativity, implies things about the curvature of space. Right? So he needed to know that a lot of that geometry that he needed to use was already developed in the previous century.
Yeah, didn't Riemann played a large role in that, his work?
Yeah, it sort of goes, Riemann, there's Lubachevsky, in the 1800s. So there's this discovery that there's a negative non-Euclidean geometry. It's also called a non-Euclidean geometry. This discovery, he needed to use that. Otherwise, you wouldn't have general relativity. So that's just one example. And as we go forward, you more recently, your cell phone, all this digital stuff that goes back and forth, and the security, the cybersecurity, and what's going on with that, that's all based on number theory.
Right.
These cryptocodes and all this, algebraic structures, and how fast can you factor a polynomial? And these are related to theoretical computer science questions. Does P equal NP? And so on.
So, and by the way, everybody, that's another episode, because that's a very deep rabbit hole in and of itself.
Yes, it is. Yes, it is. But so there's these uncanny things that happen, which is that an area of pure mathematics is developed, and then later there's an application. Maybe it's in 100 years, maybe it's in 200 years, whatever. There's an application. So the way I like to think of this whole setup is pure mathematics is like a sea. And when someone proves a theorem in pure mathematics, it goes into this sea and it mixes, and the applications are these sinkholes at the bottom. And once that application pops out, you don't exactly know where in pure mathematics it came from, because pure mathematics, like we were describing before, the areas of pure mathematics the mainstream areas all interact with each other.
Right.
So these applications come out of a result of that. So that's why often, it's for us as mathematicians, it's obvious that mathematics is important, and we're not just selfishly promoting ourselves. I mean, to us it's obvious because again, you have these things that interact, and then you sort of develop this all these structures, and it's all pure mathematics, and it's the C, and then the applications are popping out, and you don't exactly know where they're coming from. Was it topology? Was it geometry? Was it analysis? Was it differential equations? They're interacting at that higher level.
Well, and I think going back to one of our original quick chats was, I think that is the evidence that I typically use to say why mathematics is discovered and not necessarily created, because general relativity was discovered, but the only reason it really works is because of discoveries previously, not because of what somebody else created, but because of what they discovered. And again, before we go down a rabbit hole, I want to continue on your area. So when you're teaching, because right now you teach PhD candidates, correct?
Yes, that's right now. Yes.
Okay, and are you teaching them in your area of hyperbolic geometry, or are you teaching them multiple areas?
It varies. It varies from semester to semester. I mean, mathematicians this is related to what we were just saying, that pure mathematicians have to be well versed in all the mainstream areas of mathematics. So everyone teaches everything. But if you teach an advanced course or a topics course or something, you might teach your area, which I did last semester. So yes, but I'm temporarily at the graduate center. I'm the so-called chair at the graduate center. Normally, I would also be teaching it, and now I'm not teaching at Hunter because of that. But normally, I would be teaching at Hunter. I would be teaching undergraduates.
Oh, okay. And so, what would you be teaching undergraduates? What
Again,
areas
it varies. Everything I've taught. Math 100, which is the lowest area of mathematics in terms of general education course. It was probability theory, basically.
Oh, I didn't even reach that. So yeah,
it was fun for me with the Monty Hall problem and the birthday problem and so on. That was fun. Everything from there to advanced undergraduate, and we have a master's program at Queens College too, so master's level courses, so including calculus. Calculus is in there.
Well, that's what I got through. I took AP Calc, got a 3 on the test. They wouldn't accept it anything below a 4, so I had to take Calc 1 and 2 again. When over the summer, I tried to forget everything I had learned, and I had to scurry to relearn it again. I'm more fascinated that a human being was able to discover calculus, basically 2 human beings actually, Newton and Leibniz, were able to discover calculus basically within a year. And it boggles my mind that that's how their brains worked. But I strongly believe that everybody's brain works a particular way, and that just happened to be the way they worked. So I asked you this question again when we were out walking our dogs and whatnot. So I want to ask it on the record, because I believe I have my own theory on it. But do you see the world differently than the rest of us who just do, who reconcile our checkbooks and know how to calculate how much a tip is worth without having to look at the cheat sheet down at the bottom and what have you? Do you look at the world differently because of what you know of how mathematics works within the universe?
I'm not good at balancing my checkbook or
I'm very
figuring out
good at
the
that. I'm very good at reconciling. You put a
Okay.
$sign in front of anything, I'm really good at making sure it's all there and whatnot. But you put a derivative in front of me, I'm going to be, that's not happening.
Yeah, well, I think I don't think there's some unique special thing that, I think that's been sort of a theme of what I've been saying. I don't think there's some special unique thing about um, you know I think mathematicians, I think I sort of get obsessed with problems and I dig and try to understand, but there are lots of people that do that just in different venues, that kind of thing in different venues. Uh, so I don't know. Do I see the world differently?
Yeah, like when you look
Um,
at the subway tracks outside there, do you do a quick geometry on them? Do you look at
okay,
them as sort of a zero curvature? At least
uh,
I hope there's no curvature, going one way or the other.
parallel, yeah, yeah, right. Um, Sometimes, but I have to sort of like, it's sort of like a switch. I'm not sure if I would say that I go out into the world and have this other pair of glasses on all the time.
Mhm.
I don't know that I do. I think it's more, um, I might look at something, I think what you're saying might tend to be more of an artist that might see that.
Well, I think you're an
Um,
artist. I think anybody
yeah,
in the sciences is an artist to a certain extent. Obviously, it's within a
yeah,
more rules-based world than
right,
what we would think
right.
of as like a Picasso. But I still think there's an artistic flair to it and an artistic nature because you have to be creative. I mean, you said it yourself. To be able to build those structures, you have to be creative.
Yes,
You
yes,
just
that's
happen
right.
to be creative in a way very few people can appreciate or understand. Uh, because again, it's very hard to visualize what you're trying to accomplish.
It is hard. Yeah, I mean, I just that's one of the toughest questions you've asked, which is, do I see the
Yes.
world? Because I sort of have answers, I think, to as vague as they are to the other questions, but I think this one's hard because I don't know. Um, yeah, I don't know how to put myself in a different.
Well, now I hope I haven't ruined you by making you think about this all the time. Now you're
Well,
going to
now
obsess over
every time I look at the
it.
building across the street, I'm going to be thinking, okay, that building is leaning too.
Exactly. Well, hey, it is Queens, so a lot of buildings
Yeah,
lean.
right.
Our building leans.
I know
Um,
that.
but yeah, but that's why I wanted to invite you on because one, we've had great conversations, but two, I think people get frustrated by math in high school and college because I think of what you say, because it's taught in a rote manner and not as, hey, this is how you can see the universe. This is how
Yeah,
you could see anything, is if we just break it down to its mathematical elements. You can see a car, you can see your cell phone, you can see the blackboard. Um, and I've got, as I've gotten older, I've gotten far more curious than I was when I was younger because basically I was being taught so that I passed and got a good grade and got into college,
right,
as opposed to
right.
saying, well, you have Pythagoras' theorem, but what if we did this to it? And now all of a sudden it doesn't work. And you have to figure out now that it's got a third dimension. Now, what do you do? And that was never brought to my attention in a way that intrigued me like it does now.
Well, I think one of the issues that uh, math instruction has in this country is, I think, the amount of training the teachers get. I mean, there's exceptions, of course, and some of it has to do with what school district you're in. But
Mhm.
the amount of training they get and support is important. If you have someone who it wasn't the math major who's teaching a math course,
Yeah.
in high school, I think there's a problem there.
Oh, yeah. Yeah.
But it's also, there's also another aspect to this that's always amazing to me when I meet someone and it comes out I'm a mathematician. The first almost universally, maybe 8 or 9 out of 10 will say, "Oh, I hated math. I failed math." And that's really shocking because, first of all, maybe you did, and maybe you hated math and you failed, but to admit it is sort of a funny, it's like a badge of honor. And that's what
Yes.
shocks me about,
Yes.
our country, which is that I think that if you didn't do well in your English class, and if you met someone and they said they're an English professor or something, I don't think you'd quickly say, "Oh, I hated." Well, you might say I hated English, but I don't think you'd bear out all of this
Right.
stuff that's been in there. But in math, it just seems like almost, you say something about math, and there's, "Oh, I hated it," or "I'm not good at it," and I think there's an aspect of sadness to that.
Well, and I think they say they hate it because they weren't good at it. Because again, math also needs you need to, I think, beyond just teaching the rules, you have to teach the conceptualization of what it's being used for. Because when I went and I took calculus, I had a pretty good high school calculus teacher. He was also the varsity baseball coach, and he taught it well, because what he described, he showed you the funnel. When you were doing the calculus problem, it was always a funnel because it was easy to draw on the board. You draw the circle and you draw the 2 lines down. But he said, because of the curve, now what do you do? Because in geometry, when we taught you geometry, you would just, measure the angle, measure the length, and you were good. You would always get to the exact number. But you had a curve, you had a bump, you had a depression, then all of a sudden things get thrown in out of the mix. And at least he gave us some sort of conceptualization of why you were doing it. I go to college, and again, because I didn't get a 4 on the AP, I had to take it again. Well, he was just all, this is the formula, solve. And I don't know, it never sparked the interest in me until later on, where you could really see the world and realize that building over there, it's all mathematics.
Yeah.
That subway is all mathematics. That car, that bicyclist, that person walking, everything can be broken down into mathematics. And so that's where I am now. And I don't, there's no regret kind of deal. I'm pretty good at what I do now, and it just doesn't happen to be in mathematics or physics or what have you. But I get to geek out every once in a while on both topics.
Yeah. I geek out on other things too,
Yeah, exactly. Exactly. Because, well, we're over the time, and I'm going to be respectful of your time because you are running a department and doing things, but you do have other interests. You're not sitting there just agonizing over a problem 24/7, or are you?
That's right. Well, well, it never leaves you. Never quite leaves you. It's there when you go to bed. It's there when you get up. But no, there are part of it. If you're not particularly I would say, let me make a side statement in analogy with chess again. Chess is very hierarchical. If someone's better than you, they're better than you. You can improve a little bit. You can make up the difference a little bit by working harder, maybe. But they're better than you. And mathematics is also like that. It's very hierarchical. if someone's better than you, at the research level, everyone's working very hard. There's no, once you're a researcher and you're an ongoing researcher, you're working hard. Mathematics is hierarchical. If someone's better than you, they're usually better than you. And so it's hard to make up that ground of those differences. So I say that because maybe I have to work harder because I'm not in that hierarchy. Maybe, there's a hierarchy, but there's also some play, of course, because there's some people even. So sometimes I think I have to work harder. I don't particularly think I'm very talented at mathematics. I think I had some facility when I was younger, but not as talented as some of the people around me. I have some phenomenal people around me.
It was like me on the playing field. I was talented to a certain level. And then I could work harder and get to another level, but I was never going to get to the ultimate. I just didn't have that. I just didn't have that talent, no matter how hard I worked.
What sport are you talking?
Any sport.
Oh, yeah.
I mean, I'm addicted to any sport. I mean, I watch competitive grass growing if I could.
Okay.
So, but.
Well, you're right. It is
very much like that.
So when you get to the levels of baseball players and, it's hierarchical. When you get to those level, minor league, major league, and then within the levels of the major leaguers and within the level, it's hierarchical. There's some, when I say that, I don't mean to say that there's an exact ordering, because it could be that a whole bunch of people are around the same level, but then there's another level.
Yeah.
Another level.
Yeah. Well, in today's parlance, there's Mike Trout, and then there's a group just below him.
Right.
And then there's a wider group below that group, and then you get down and so on and so forth. But I guess that's a topic for episode 2 of our conversation, because you did offer to draw something, and I think I want to do another episode down the road and have you draw out some of the things that you work on.
That's fine.
I think that would be really intriguing, but we've already exceeded our time limit, which I knew we would. That's all my fault. But I really want to thank you for doing this. This was
a
great conversation. I hope we do an episode 2.
This was good. This is very good.
Glad
Thank
to
you.
hear.
We can do an episode 2.
Ah, fantastic. So you heard it here first, folks. He's agreed to do an episode 2. I'll make sure I get that scheduled. So I want to thank you again for joining us. Everybody who joined, did you know that? ? I want to thank you again for doing so. If you haven't already done so, hit the subscribe button with the bell. If you've liked this episode or any previous episodes, be sure to hit the like button and leave some positive feedback. It's always welcomed, again, to help grow the channel. And Ara, until the next time I see you out with the dogs, you take care, and everybody out there in the cyber world, you as well. Until next time, see ya.